is Friday, and I promised we would get a little more interactive today, so we are going to get to Tinkercad in a minute. But first, I wanted to try something. We have now done several activities where we tried to get you guys to see if ChatGPT could do the assignments for this class, right? This is a college-level thing, not just at Cornell, but universities nationwide, trying to figure out how to kind of grapple with how do we integrate generative AI into the curriculum, because as a reality, people are going to be using it going forward, you're going to be using it at work, so how do we kind of work it into the class? I am curious if ChatGPT can do my job. So, what we have here, I have not hit enter on this prompt yet. I teach Mechatronics, MAE 3780, a junior level engineering class at Cornell University that covers analog circuits like resistors, capacitors, etc. Their applications like filters and motor drivers, and a microcontroller component where students use an Arduino Uno and build a robot to compete in a tournament. I need to give a lecture on analog to digital converters. What I didn't type in is that it's Friday, it's nice out, and I don't really feel like doing my job, so we're going to see if ChatGPT can do it. That covers how they work, shows the basic circuit diagram, and does a demonstration using an Arduino with the analog read function. Can you write a script for a 45-minute lecture for me that also includes any diagrams I need to show? Let's find out. Enter. Failed to generate. Seriously? You'll need to log into ChatGPT. Okay, so the free version doesn't want to give me a full 45-minute lecture. Screw you, ChatGPT. I guess I'm going to have to do this myself. I did actually come prepared, okay? I wasn't just going to stand here and read a ChatGPT prompt to you guys. So,
log in.
Maybe, well, yeah, if I log in, you guys are going to see my history over on the left, right? Not going there. Okay. Maybe I will try this again for next week. I just call, just make sure it's not my daughter's school or something. Okay. All right. I did, actually, in advance, I was curious how this would handle image generation. So, I'm going to post these slides so you don't have to bother copying down the whole diagram. All right, let's back up for context here for a minute. Why are we talking about analog to digital converters at all? So far we have mostly been dealing with the digital pins on the Arduino, right? Everything is either high or low. There are sensors and different things out there that are analog, will generate a continuously variable voltage, somewhere between 0 and 5 volts. And there are analog pins on the Arduino that can read that voltage, just like your multimeter can read a voltage, right? Can we get a pause for Rashika to hobble across here? Okay. Have you been to a doctor yet?
No.
Okay, so that's where we're going today. Is this may or may not be something you want to include in your project. For many teams, if you already kind of have your design at this point, you might not be ordering an analog sensor, but I want you to know how analog inputs work going forward, even if you don't use it in your robot project. So that raises the question of, okay, how exactly does the Arduino measure an analog voltage? How does it know something is 2.3 volts instead of just 0 or 5 volts? And rather than drawing my own circuit diagram, I went to the internet and various generative AI services to see if they could do it. So if you just Google analog to digital converter circuit diagram, kind of conventional Google image search, it will bring up something like this, right? So again, don't bother sketching all this down now. It's going to be in the slides, but this shows a lot of things we have seen in this class already, okay? So looking at this kind of from left to right in stages. First, I have a voltage divider, but it has multiple resistors in it. You know, there's more than just 2 resistors. And what happens there, for example, in this diagram, if I have a 4-volt reference voltage fed into 4 equal size resistors, it's kind of going to break that voltage up. So I'll have 0 volts, 1 volt, 2 volt, 3 volts. Okay, it breaks it up into different increments. I then have a separate line, so that's my reference voltage, that's constant. I have a separate line feeding in an analog input signal. So that's just whatever my voltage coming from my sensor is, that can change. Each of those are then going into the inputs on a comparator, right? So this comparator is taking that fixed 1 volt as one input and my varying analog input as the other input. This comparator is taking 2 volts as a fixed input, and then my varying analog input, and so on. So basically, if I start that analog input out at 0, and then gradually increase it, these comparators aren't going to flip until it exceeds each corresponding threshold voltage, right? When it exceeds 1 volt, then the output of this comparator is going to flip. Remember when we did this with the comparator exercise, with a moment one voltage exceeds the other one, then the output would swing either high or low, depending on which voltage was greater, right? So as I keep increasing my analog input voltage, the comparator, the output of the comparator is going to switch, and then that's how you kind of get this from an analog to a digital signal. We're not going to worry about what exactly the encoder part is, but that's the basics of it. You have this ladder or series of resistors that divide the voltage up, and then you use a series of comparators to compare your input voltage to a series of threshold voltages. So again, thinking about the AI side of this, that's what the diagram should actually look like. I was curious what different generative AI services would do if you asked them to produce this diagram. ChatGPT at least produces a real circuit diagram if you ask it. Okay, this is not the correct diagram. It did at least draw an op amp, and it has an analog in and a reference voltage and the digital out. But if you look at this op amp circuit, this doesn't actually make sense. Remember your ideal op amp assumptions. We do have negative feedback. If we have negative feedback, then the positive and negative inputs are going to be equal. And notice how it drew a capacitor symbol there instead of a battery symbol, right? So it didn't get the reference voltage quite right. If these two voltages are equal, then it's shorting my analog input to my reference voltage, right? No current drawn there, so the voltage here has to be equal to my reference voltage. That's just connected directly, so my analog input voltage. So again, it didn't, at least it drew a circuit diagram using correct symbols and spelling and everything, but it didn't actually give me the right circuit diagram. I think next up I tried Gemini, which gets a little more abstract. Like, it kind of drew a circuit diagram, but I guess clearly the way it's handling text is different. Like annals to like, it didn't actually spell correct English words, and it threw it like quantizer. There's a bunch of other crap just in here. So like, kind of passes for a circuit diagram, but definitely not what we were looking for. And then Copilot, which I guess Microsoft split off into a separate thing called Designer, at least for the free version, totally did not get the memo and just kind of produced arts. Yeah, I mean, like, it gave me 4. I forgot to put all of them in there, but it gave me 4 different diagrams, kind of like this, where it was like this weird, like, old-timey sketch of like a circuit, but clearly not what I literally wanted for an analog to digital circuit. So my hope was that it would also give, ChatGPT would have given me a script to kind of go along with these diagrams, but again, I did actually come with my own lecture and was not just going to bank on ChatGPT for today. So, let me think, look at time. And I promised Tinkercad for today, so let's do Tinkercad first, and then we'll switch to the paper notes at the end of class if we have time after kind of the initial Tinkercad setup. So, pull out Tinkercad, and I don't have a starter circuit live for this one yet, so you're going to have to kind of start a new one and follow along. I'll give everybody a second to get this open. Okay, so get your basic circuit set up with an Arduino and a breadboard, and we'll go from there. Okay? All right, things you should be familiar with by now: connecting power and ground, which is again something you need to be careful with when wiring your H-bridges. Okay, I realize people are still kind of unpacking laptops and stuff, so we'll give you a minute to catch up to this point. Get your basic starter circuit going with the Arduino, breadboard wired, switch over to the text code, and our kind of standard starter code with the main function and the while loop. So if I can zoom in on the text, that's already as large as it gets. Okay, again, I'll give everybody a minute to get there, so I try not to get too far ahead. All right, we are actually going to add something to the circuit first. So potentiometer, you've used potentiometers in the homework before. It's been a while. Okay, this is like a variable resistor, but it has 3 terminals. Okay, so the resistance between the outer 2 terminals is fixed, and the resistance between the middle terminal, called the wiper, and either of the 2 outer terminals changes when we change the knob, right? So you're going to put that in the breadboard. So the 3 pins are in 3 different rows. Hopefully you know how a breadboard works by now. You don't want to do that if the 3 pins are shorted together. Okay, put it in 3 rows in the breadboard. I want you to wire one of the outer pins to 5 volts, the other outer pin to ground, and then connect a multimeter to measure the voltage of that middle pin. Okay, so my multimeter is going to be referenced to ground. Okay, give everybody a minute to do that. Potentiometer in the breadboard, 2 outer pins to 5 volts and ground, multimeter to measure the voltage of the middle pin. Pardon me for checking my phone, but I have a missed call from my mother-in-law who is watching my daughter right now, so I just need to make sure everything's okay. All right. Once you have that set up, without even running any code, you should be able to start the simulation and then see the voltage change as you turn the knob, right? It should go between 0 and 5 volts. Okay? So not even worried about any Arduino code at the moment. This is going way back to what we did at the beginning of the semester with a voltage divider. The potentiometer is just acting like a variable voltage divider where it's changing the knob, and it's changing both the resistances at once and kind of gives you a linearly changing output voltage with the rotation. Okay. Any questions on kind of the potentiometer or voltage divider side of this? Nope. Okay. All right. That is how we hook up a multimeter to measure the voltage. Cool. We want to get that into our Arduino. Okay. To do that, we are going to use one of the analog pins labeled A0 through A5 over here on the left. So pick one, doesn't matter which. Oh, I'm going to stop the simulation or it won't let you add wires. Okay. Wire that to the middle pin. And pick an arbitrary color. I don't know, I'm going to use green. Go over to your code. Okay. This is going to be the one time in this class we let you use just the Arduino function to make life easier, because doing this with registers is really complicated and I don't have time to devote a whole lecture or two to it. So you need to do a couple things. First, we are going to declare a variable for our analog input or sensor reading. So int, call this whatever you want. I'm just going to call it sensor. Okay. So declare variable sensor reading. We're just kind of using the potentiometer as an example because it's simple to wire, but this would apply to any other analog sensor. If we have time today, we'll get to an analog temperature sensor as well. Okay? So inside the main function, as usual, we have our code that only runs once. We need to call the Arduino init function, which is required for analog read to work. Okay, so init doesn't have any arguments like that. This function is normally called as part of the Arduino setup function, which we are not using. It initializes a bunch of register and timer values and things that then enable a bunch of Arduino libraries and functions to work. So normally we're not using that because we don't need it, but if you don't call that in your main function, then analog read won't work. Okay, the risk of doing that is that I honestly don't know what all the default things it's setting are. You'd have to go dig into the Arduino source code to find out. If you then manually set all your timers to do other stuff with PWM or the color sensor or whatever else we're doing, there's a chance it will mess up analog read. So this is something that kind of works well on its own, but when you start mixing and matching registers with the Arduino code, then there's a chance you're going to run into conflicts. I have not tested that extensively to see which conflicts you get with which timers or what, but kind of a general heads up that things can get weird. Okay? And then, all we need to do in our while loop is set our sensor variable equal to analog read, so that's lowercase analog and then capital R read. That's the Arduino function for whichever pin we have it connected to, which I used A0. So I'm going to put A0 in there, close parentheses, semicolon, and after that I'm going to want it to just print this value out. So I'm going to add, as usual, my serial.begin 9600, semicolon, and serial.println sensor to print out that variable. Okay? Give everybody a minute to catch up on that. Oh, I forgot the L in serial. All right. Then, when you run that, you should open the serial monitor and look at what happens when you change the potentiometer. And what do you notice? Does this number match that number? No. Does anybody know why?
Overflow error?
Nope, not an overflow error. Back?
It's on a 0 to 1024 scale.
Yeah, so 0 to 1023 scale, not because it starts at 0. So the Arduino's analog inputs are what's called it is a 10-bit analog to digital converter. So it is not going to give me 3.9 volts. Using kind of that circuit I showed earlier that was just for a few bits, it has 10 bits. So it is going to convert it to a 0 to 1023 just digital number, which is going to correspond to the voltage, right? So if it was an 8-bit digital converter, it would only go up to 255. If it was 16-bit, it would go up to 65,000, whatever. Point being, the more bits you have, the better resolution you get. So if we want to actually convert this to the voltage, then we need to do a little more math, right? So if I go in here and create, sorry, let me start again. So you should see when I crank it all the way up to 5 volts here, then this goes up to 1023, right? So this is proportional to the voltage, but there's a conversion factor between them. When I go down to 0, it's 0, and I'm roughly halfway. 511, I'm roughly halfway, right? So if I create another variable for my voltage, say int voltage, and then I'm going to change that to just print the sensor value, and I'm going to say voltage equals, okay, sensor divided by 1023, so a fraction of 1023 times 5, which is my max voltage. So in theory, if sensor is 1023, right, then that'll just be 1 times 5, and it'll output 5 for the voltage. If I'm roughly halfway, it'll output 2.5. If you know where I'm headed with this, don't spoil it for everybody else, though. Okay? Ideally, that's what it would do. So I'm going to print out a little space. And then I'm going to print out my voltage. Hopefully. Give everybody a second to catch up there. except that's odd. I am always getting 0 for the voltage unless I'm all the way up at 1023. Okay. Anything less than 1023, it's printing 0. Anybody know why it's doing that? It's red shirt in the back. It's got to be a float, right? So this is where you have to be careful with data types in C as opposed to MATLAB or Python, where you've probably dealt with this previously. I told it that both sensor and voltage are integers, meaning they cannot have decimals, right? So for anything less than 1023, this initial operation it does, sensor divided by 1023, it's just immediately going to truncate that down to 0. Okay, so 1000 divided by 1023 is 0 point whatever. It just truncates that to 0 and then multiplies 0 by 5 and always gives 0. So this is where, a couple caveats here. Order of operations and variable types, and then I also don't know if there's a difference between how this will work in Tinkercad and on a physical Arduino. Things can get a little weird. So for example, if I do the 5 times sensor first, okay, mathematically that shouldn't make a difference, right? But now I am first multiplying 5 by my sensor reading, so it could in theory be a number bigger than 1023, and dividing it by 1023 should no longer give 0. Okay, but I don't actually know. Let's see if that works. Okay, so there. See, now it kind of gives me this very coarse resolution where it'll just go 0, 1, 2, 3, 4, 5 volts, but it's not giving me a decimal, right? But all I did, again, mathematically, in terms of what we learned in algebra class in middle school, right? Moving that 5 at the beginning or the end shouldn't matter. Here it does, because now the C program is doing that operation left to right. So that number is still an integer, but it's now big enough that I can divide it by 1023 without getting truncated and going down to a 0. Okay? If I actually want to get a decimal place on my voltage, then I should be able to change voltage to float, which is the data type that will allow for decimal places. Okay? And now, what's interesting there is it is still showing the zeros, and this is where it gets a little weird with data types. There is some hierarchy for promotion, or how if you have an equation with 2 different data types. So I'm trying to assign a float equal to some equation that depends on an int. And this is a better question for a true computer science person in terms of what C will actually do with the different data types. So if I change sensor to also be a float, even though analog read is only going to give me an integer, it's only going to give me 1023, not 1022 point something, then now I will actually get decimals. You see 3 point something, 2 point something on the voltage. So yeah, it's a little weird with the data types. The downside of doing this is that math with decimals takes longer. You know, microcontroller is much more resource constrained than something like a PC, so multiplication, division, all of those things using floats as opposed to integers takes longer. Maybe for the code we're running here, just with the potentiometer, kind of on a human time scale, doesn't matter, but on a computing time scale, that can take a really, really long time. So depending on what your program's doing and how fast it needs to go, the general rule of thumb is you kind of want to avoid floating point math and stick with integers. So that is going to depend on, you know, what you're doing, what the application is, and what you actually need in your code. Maybe you don't actually need that voltage and you can just work with this number. If it's just a threshold, for example, if you want to turn a light on when the potentiometer voltage exceeds 2.5, right, then you don't actually need to calculate that 2.5 in your code. You just do an external calibration with your multimeter and look at, okay, when that voltage is 2.5, then my analog read value is 511. So my code is just going to be if sensor greater than 511. Right? And then I can keep sensor as an integer and I never need to bother doing this. Okay, so Again, not necessarily, I did have at least one question about an analog sensor for a robot, so I wanted to cover this so we're all kind of on the same page and level playing field if anybody wants to use them. If there is some analog sensor you want to use. Another option, for example, is I showed those graphs last time of the QTI sensors and how ideally you have your sensor positioned such that you have a logic high on black and a logic low on blue and yellow, but it in truth is actually an analog output, right, that can be continuously variable. So if you wanted to use, analog read on your QTI sensors instead, you could. I'm not saying you should, not saying you have to, but that's another example of where you could use this. Okay, so we have about 20 minutes left. We're going to switch over to the paper and pencil stuff for a little more theoretical explanation about this, but I wanted you to have the Tinkercad code up so you have it, again, if you don't use it for this class, so you kind of have it for future reference. So and again, as usual, I'll post a better commented version of this on Canvas. I'm not going to type out all the comments now. But questions on this? No? Okay. We are going to switch over to the document camera. All right. So in general, kind of earlier in the semester, right, we were talking about analog voltages all the time, and now we've mostly been doing digital stuff with the Arduino. But for an analog signal, it basically means it can be continuously variable, right? So if I have a graph of voltage versus time, it can take on any value between the min and the max as opposed to only being either high or low. But for an analog to digital converter, we can't sample it or get readings infinitely fast, right? It takes some finite amount of time to do what we just kind of glossed over. You have that circuit diagram with the op amps that's physically reading the voltages, and then you have the analog read function, that's the code that's converting that into ultimately a number in your code. So what you're actually doing is kind of sampling, it's called sample and hold, where you grab a value, it takes some fixed amount of time to kind of do the conversion, and then you grab the next value. So you wind up kind of getting this chopped up, and draw this really chopped up or digitized version of the analog signal, right? And the faster you can sample it, then the more accurate that's going to be. Technically, I'm going to draw this really exaggerated, right? If I am sampling it this frequency, then these are the only data points I know in my code. There's no way for me to know that the analog signal didn't actually do this, right? But I wasn't sampling at a high enough frequency to catch those higher frequency oscillations. So general rule of thumb, which is called the Nyquist criteria, is to sample at least twice. Sample at least twice the highest frequency you expect to have in the signal. And this may not always be something you have direct control over. There might be a ceiling depending on the hardware you're working with. So honestly, I would have to go look up what the maximum analog read sampling frequency of the Arduino is. But the Arduino is actually kind of old hardware at this point. The platform is more than a decade old, so there are probably newer, faster microcontrollers out there that can sample more quickly. But usually when you're working with a microcontroller, you're going to have some maximum rate that you can turn that up to. Okay? And we kind of just demonstrated this in Tinkercad, but in the analog domain, you have some zero, say we're going to use 0 to 5 volts as an example, because that's what the Arduino can do, right? Then you convert that to the digital domain, it's going to depend on how many bits you have for the resulting numbers that you can get out. So for example, if we just had a 2-bit ADC, then in binary, the only possible values for that ADC are going to be 0B, 00, 0B01, 0B10, and 0B11, right? Or in, so that's in binary. Or over here in decimal, that's going to be 0, 1, 2, 3, right? So remember, it doesn't go up to 5. It's not going to give me 5 volts for an analog voltage of 5. In this case, it's going to give me 3. And kind of, depending on how exactly that circuit with the capacitor, sorry, with the resistors and op amps is working, kind of anything below the corresponding threshold here is going to turn into a digital 0. Anything here, you get the idea, right? So there's going to be thresholds here where kind of a bigger chunk, so roughly a range of, I don't know, 4 to 5 or 3.5 something volts is going to read as high there. And then the more bits you have, so again, if this is 10-bit like the Arduino, then it's going to go all the way up from 0 to 1023. Whoops, wrong. 1023. So there I get much. I'm not going to draw over 1,000 lines there, right? But I get much finer voltage resolution. So I think if you do the math for that on the Arduino and divide 5 volts by those 1023 divisions, you get about 4.887 millivolts is the finest increment you can measure, right? So roughly 5 millivolts. If you have an analog signal that changes by 1 or 2 millivolts with a 10-bit ADC, your resolution isn't good enough to see that change. Okay, any questions on that? All right, so we've only been talking about the voltage and then the corresponding ADC value, but there's a whole world of analog sensors out there that measure different physical things, right? Temperature, pressure, force, acceleration, whatever it is. So ultimately many times you're interested in what is the actual physical measurement or quantity. So there's kind of a third step there. So far we've been talking about, so you have the actual analog voltage, which in our case for the Arduino is going to be between 0 and 5 volts. You can convert back and forth between that and the ADC value, which in our case is 0 to 1023, specifically for the 10 bits on the Arduino Uno, right? That could be different for a different microcontroller with a different resolution ADC. But then you also might have a conversion factor between whatever the physical units are for the sensor. So it could be degrees C, meters per second squared, newtons, whatever, it depends on the sensor. And that is where you need to get this from the sensor data sheet. Okay, so I don't bother writing this down. I'll try to copy all of this down and just scan this as part of the lecture notes later. This is an example for an analog temperature sensor, which I think we'll have enough time to switch back to Tinkercad to do this real quick, where it gives you, as usual with data sheets, a ton of information, but we don't need all of it here. We specifically want, let me see if I can get this in a different color. For example, for the TMP36, which is the specific model temperature sensor we're going to use in Tinkercad in a minute, it gives us a scale factor of 10 millivolts per degree C, which means for every increase in degrees Celsius we have, then the output of this sensor is going to increase by 10 millivolts, right? But sometimes there's also an offset, so you have to figure out where the 0 point is. It does not necessarily mean it's going to be 0 volts at 0 degrees C. So somewhere else down here, we have output. Output voltage at 25 degrees C is 750 millivolts. So if we want to have kind of a line or a graph that shows us, okay, on one axis it's millivolts and on the other axis it's degrees C, this isn't necessarily correct, right? There's basically going to be a calibration curve with some slope which is what we get from that scale factor, millivolts per degree C. And then it gives us not necessarily the zero or intercept, but some point on this line. So somewhere at 25 degrees C, we're going to have 750 millivolts, right? And so this specific information is what you're going to need to look up specific to the sensor you're using. Okay, it could be, maybe it's not linear, maybe it does go through zero. Point being, that has to come from the sensor data sheet to ultimately allow you to convert between what we're talking about here. Your code gives you this, right? The ADC value between 0 and 23. The sensor's data sheet gives you this relationship, so you need to then, if you want to have your Arduino, I don't know, you're building a little Arduino weather station and you want it to display the temperature in degrees C or degrees Fahrenheit, right? You have to get back to there from your code. Okay, and I think we have 10 minutes left, so I'll give everybody a second to finish writing, and then we can switch back to Tinkercad to do that with the temperature sensor real quick. Questions? Getting you guys to ask questions is worse than like asking my kids what they want for dinner and trying to get an answer out of this. Okay, a minute to finish writing, and then we'll switch back to Tinkercad. If you're done writing, copy your potentiometer circuit so you don't overwrite it and start a new one. And we will then modify it to work with the temperature sensor. Okay, still see some writing, so I'm going to wait for a second. If you want to work ahead, go into Tinkercad again, create a copy of your circuit, name that one potentiometer, analog read, or whatever it is. Look for the TMP36 temperature sensor in Tinkercad, and you should be able to basically slot that in where the potentiometer was. If I remember the pin out correctly, it should work the same way where you have power, signal out, and ground. Okay, I'm going to switch back to Tinkercad. As usual, if you didn't, I'll post the notes if you didn't get everything there. All right. So, I'm going to go to my code. It's right there in the default TMP. So we have power, V out, and ground. I'm just going to delete my potentiometer. Slot the temperature sensor in, so nothing else changed, right? Which is just lucky because the pin out of the temperature sensor matches up with the pin out of the potentiometer. So now if I start the simulation, I get this little temperature slider. And since we can't actually change the temperature in Tinkercad, it kind of lets you simulate it by driving this slider back and forth. And note that the output voltage does not go between 0 and 5. This was something else that I forgot to mention in the data sheet. The output range of this thing is only from about, I think, 100 millivolts up to almost 2 volts. That's just how the sensor works. It doesn't have, so that would allow it to work with a lower voltage microcontroller. Again, there are microcontrollers out there that only use 3.3 or 1.8 volt logic levels, so it would be compatible with those as well. But we would need one more line of code to actually convert to temperature, right? So I'm going to create another float variable called temp. So I have my sensor reading, I have my voltage. I'm actually going to convert voltage to millivolts instead of volts, so make that a 5,000 instead of a 5. And then one more line of code, which again comes from middle school algebra, just the equation of a line. 25 plus voltage minus 7, there's probably more than one way you could write this, but I didn't bother going through all the math, but remember this is converting our voltage, that should be a 750, not a 75, excuse me. That is converting our voltage in millivolts to temperature in degrees C. So 25 was that offset where we know it's 750 at 25 degrees C, and then we have that slope of 10 millivolts per degree C, which we need to invert here because we want degree C as the output, right? So that is just one more line converting voltage to temperature. So we should get now, if we add another serial print, print out the temp, and run that, and unless I screwed up, okay, we should now get a last line here that's very close to the temperature it's actually showing for the sensor, right? Again, this is simulating a fake temperature in Tinkercad, but if I move this slider, okay, then we now see how I have taken the physical temperature from the sensor, converted it to that ADC value, which is between 0 and 1023 using the analog read function, converted it back to voltage using the scaling for this specific ADC, where 0 to 5 volts corresponds to 0 to 1023, and then converted that voltage back to an actual temperature in degrees C using the information from the data sheet. Okay, so this is just using that particular sensor as an example, but the same process would apply to any other analog sensor. If you want to buy an analog accelerometer for your robot or force sensor or whatever else it is. Okay, where again, depending on what you're doing, you would need to think about whether you actually need this number in your code. If you can just do an external calibration with a multimeter or whatever it is, and then figure out where the thresholds or values that you care about are, then maybe you're just fine with the ADC value and you don't actually need to bother doing those additional calculations, which are going to slow your microcontroller down because floating point math is slow. Okay? Any questions? Somebody give me at least one question today. No? You guys are killing me. Yes?
How's your day going today?
My day is going great, thank you. It is sunny and I am looking forward to going outside. Hope you guys are too. Okay. All right, in that case, no more questions. We are done a few minutes early. As usual, I'll be here if anybody has questions you want to ask after class. I think the last time I checked, there were still a few teams that needed to do milestones 1 and 2, so obviously make sure you get those done today if you have not already. And milestone 3 gets harder, so if you haven't started thinking about that yet with your color sensors and your QTIs, be prepared for next week to be harder than this week, okay? Thank you.